Okay, welcome to my presentation. Thanks for coming. So I had this awesome idea of taking a car from Beauvais Airport yesterday and driving here. And then, there's no place to hold your phone, so you keep your phone on your laps and you have this navigation. So you sneak a peek from time to time to get some instructions, but generally you listen to it. And then I got to Paris. And it told me, take right. And it's like, which right? The road splits into 1, 2, 3. Which right is right? And so I thought it was a little bit ironic because it took me 4 hours to get here yesterday. But it's also good because I can still see there's like a massive application of maps and map processing and routing. So let's talk about it. Sorry. Where's the receiver? Yeah, I was given this one. Can I? How does it go back? Ah, this one. Okay, sorry. So the initial motivation for giving this talk was that I was recently involved in a project where we were evaluating the value of a location based on amenities around it and the proximity to these amenities. And I thought that when you get into map-related subjects, the learning curve at the very beginning, because before you get really into the domain, is pretty steep. So I thought it would be good to talk about it to give you some quick start. And well, first of all, we have this navigation that leads you from Paris and you take up too much time if you make mistakes, and there are maybe some need for cognitive services included in maps, or better cognitive services. But clearly, we are living fast. We want to commute fast. We don't want to waste time. We want to make most of the castles around us when we are holidays and things like that. On the other hand, there is also data available these days, so we have all the geographical data available. And even though this data is huge, we have computing powers at hand as well. So in typical setting, routing, well, I'm going to talk about routing. So in typical setting, we have 2 use cases. One is to find the optimal route from point A to point B, like from this airport or the other airport to here. And the other one is to, among all possible places of a given type, find the one which is the closest to you. And so sometimes it can be like just one bar to which you want to navigate, and this is taken from this project that I was involved in. So we were taking the isochron for the area where a pedestrian could get within 10 minutes, and within this area we were looking for all the amenities of specific types. And well, sometimes it is exactly one bar, sometimes it is 191 restaurants. And for each amenity, we were calculating the walking distance, so like exactly the path. Okay, so in terms of data, we decided to use OpenStreetMap. And OpenStreetMap is a collaborative project where people can voluntarily edit the map of the world. It was started in the UK in 2004 to provide an alternative to commercial data. And actually, it's pretty accurate. Of course, the accuracy varies, and it depends on popularity of OSM in a given country and among given people. But it's pretty decent, I would say. Let's talk about this OSM in more detail. So there are 3 types of elements. There are nodes, which correspond to just like a single point, like a shop, a bus stop, mountain peak, etc. There are ways that can be like roads, footpaths, roundabouts, or a building outline. So in these 2 last cases, this will be like a closed way. And finally, we have a relation. And so if you think of a university campus which has several buildings, this whole campus is a relation of these buildings, of these elements, is a collection. So if we look at a typical node, it has an ID at the top and latitude, longitude at the bottom. These are like a mandatory things. But on top of that, we can have additional data like address, name, opening hours, etc. And using this data, you can select the nodes that are to your interest. For example, here I was selecting the main train stations in Berlin. And basically what it does, it looks for all the railway stations, subtracts subway, subtracts city rail, and then finally looks at the category of a station and picks category 1 if any is given. And that way you can get the nodes which are actually interesting to you. Then we have ways. So here, again, in some area of Berlin, I listed all the ways that were present in this area with their types, and so here they are, and they actually constitute a routing graph for us. So in a routing graph, we have nodes and we have edges. So and the OSM array is basically an ordered sequence of nodes connected with straight line segments. So these nodes will become nodes in a routing graph, and line segments will become edges. Each edge has a direction, and each edge has a weight, and this weight is basically a distance between these edges, between these nodes. Okay, but not all ways are walkable, or not all ways are suitable for transport. So we can exclude them, for example, removing the outlines of the buildings. I mean, parkour is pretty, it came from France, right? So you should have some experience with it, but I'm terrible. So for me, it is impossible, so just these. And for cars, it is even a smaller graph. I guess there should be like metropolitan motorways with pretty low weight, so that I never go there again. And okay, so now we have nodes, we have edges, we have our routing graph, and we want to route through it. So I did some initial research, and I found a lot of quotes or statements like that, oh, don't be stupid, don't use Dijkstra's, use A-star. I was, okay, I'm not that stupid, right? So A-star is pretty fast. Its complexity depends only on the number of edges, and it is so-called an informed search algorithm because it looks where your destination is and kind of discards all the ways that are going in a different direction. And so here I wanted to go from A to D, and there are some weights here. So like on top left is a distance from the origin. Top right is the optimistic distance to your destination. So like, for example, a straight line distance to your destination. And then you actually look at the sum of these two components. And the algorithm just traverses the graph, picking the smallest weights. And then here it basically visited only these nodes which are exactly on the optimal path. Well, so I had this algorithm which was fast, and everything was supposed to be perfect, only that it was terribly slow. And that made me realize, or some additional research made me realize, that the problem A-star solves is how to get from point A to point B. However, my problem was a little bit different. I wanted to find routes from 1 point to 191 restaurants. So how about Dijkstra's? So first impression, it is slower. And if we look at the same graph as before, the optimal path was found again, but there are also these nodes in orange, and these are the nodes the Dijkstra's algorithm visited as well. And there are weights for the nodes, but you can see only one number. And this is because in Dijkstra's, the only measure which is taken is the distance to the origin. But here's a trick. If you visit a node with Dijkstra's, you can store this information and reuse for another destination. It never changes. But with A*, if you change the destination, even though you visited this node before, you have to at least recalculate the optimistic distance. So you actually, for many destinations, you have to actually keep computing things. And so I started wondering, okay, A* is faster, Dijkstra is slower, A* is for one-to-one, Dijkstra is for one-to-many, but where's this boundary, where's this threshold? So like, if I was always dealing with small number of amenities, with small number of destinations, maybe I don't have to bother with algorithms and just take one. But how small is small? So I decided to investigate this problem, and I ran the comparison tests between these two algorithms. And I ran it on this kind of city graphs. So again, within this 10 walking minute boundary. And I was repeating the execution of each algorithm 100 times for a specific number of destinations. So here, hopefully you can see it. The Dijkstra is red and A* is green. And the scale is logarithmic. So actually at the very end it is 128 edges. It's like powers of 2. And I put the additional point with 3 destinations because this was where the swap was happening. And yeah, so for Fontenay-Trésigny, which is this village up north, and we had the swap around 3 and 4. This is a pretty small graph because it only has 1,100 vertices and around 2,500 edges. But what about bigger graphs? So here, in addition to checking on the size of a graph, I also was curious whether the shape of a city makes any difference. Because in Fontenay-Trésigny, it's more like a naturally growing village. And here we have some administrative decision that everything is going to be grid-like. So does it matter? It turned out that it doesn't really matter. This graph is 7,000 vertices and 16,000 edges. I will zoom in. So here is linear scale, so from 1 to 8. And this swap again happened between 3 and 4 destinations. And finally, the biggest graph, and again a different structure of a city, this time as a circular. And the graph has 8,000 vertices and 18,000 edges. And I will zoom in again. And here the swap happened even earlier. So like a takeaway is that, okay, at the very beginning, A* is faster because it just goes to the specific destination, and Dijkstra does some redundant work. But at some point, Dijkstra just calculates the whole graph. So getting the optimal path to yet another destination is just like looking it up in a hash table. So it's immediate. So to take away points, you actually, I think you get it. If you have very few destinations, you can just use A*. In case of 191 restaurants, you should rather consider different solutions. And so I hope that with this guidance, you will now solve my problem of getting from Beauvais Airport to this conference next year so that I don't have to spend 4 hours in a traffic jam and make wrong decisions just because, well, which right is right. Thank you.